So good afternoon. I'm Dan Freed from the University of Texas. Happy to welcome you to this week's ACP colloquium. The talk will be about 50 minutes and then we'll have discussion questions afterwards. So unless it's very pressing, if you can wait until then. And those of you well, I left you some wiggle room with what's pressing, but that's what you prefer.
I just thought it might be simpler between the Zoom questions and the in-person, but
okay, well, if in the room you have some questions, and on Zoom, you can feel free to use the chat or raise your hand after the lecture, and we'll get the questions that way. So our speaker today is Vivienne Baldassare. Her PhD is in astronomy and astrophysics from the University of Michigan. She was a postdoc at Yale and now is the William Band Distinguished Assistant Professor at Washington State University. And today she'll tell us about the search for massive black holes in dwarf galaxies.
All right, thank you for that introduction. I'm so happy to be here in Aspen talking to all of you in person and over Zoom about the search for massive black holes in very small galaxies. Okay, so I wanted to start off with a bit of an overview on black holes and the different types of black holes that we observe in the universe. So we observe two different general categories of black holes. We have stellar mass black holes. These are black holes that we know form from the deaths of very massive stars. So stars that are roughly 10 times the mass of our sun and larger. Our galaxy alone is thought to contain about 100 million stellar mass black holes. These can weigh a few times the mass of our sun, up to about 100 times the mass of our sun. And the closest one of these stellar mass black holes to us that we know of is about 1,000 light years away, weighs about 5 times the mass of our sun. You may have seen the recent LIGO gravitational wave detection of the merger of two relatively massive stellar mass black holes. So this particular discovery is the largest of this category of black holes that we know. The two black holes that merged together were around 60 and 80 times the mass of our sun and gave us a remnant that is about 150 solar masses. This was a really exciting recent discovery from LIGO. And again, this is the largest of this class of stellar mass black holes that we know of. We also observe supermassive black holes. So these are black holes that live at the centers of galaxies. They can weigh millions or billions of times the mass of our sun. So this picture on the right there is of the giant elliptical galaxy M87, relatively nearby to us, that has a black hole upwards of 1 billion times the mass of our sun. And sometimes we observe black holes that at the centers of galaxies that are very active. They're consuming lots of material and there's lots of light emitted from the center of those galaxies. And then sometimes we have relatively quiescent black holes that aren't consuming a lot of matter, and those can be more difficult to find. And this particular galaxy, M87, is the galaxy where we have imaged the event horizon of the black hole at the center. So this is the image from the event horizon collaboration of the event horizon around the extremely massive black hole at the center of M87. This happens to be a relatively quiescent black hole, We think that it did have some, definitely had some activity in the past, but it's currently relatively quiet. Then, of course, we have the black hole at the center of our own galaxy, the Milky Way. So perhaps you've seen this video. This comes from Andrea Ghez's Keck UCLA Galactic Center Group. The Physics Nobel Prize last year went to Reinhard Genzel and Andrea Ghez for their studies of the supermassive black hole at the center of our galaxy. This is probably my favorite animation in all of astronomy. It shows us the orbits of stars at the center of our galaxy, which those two groups have tracked over the course of over 2 decades now. And we can see all of the stars in this animation orbiting around a common center of mass. And based on the velocities and positions of these stars, we've been able to work out that the black hole there is about 4 million times the mass of our sun. I think this video also illustrates something very important, which is that when we search for black holes, we're always looking for the impact that the black hole has on the material around it. So in the case of our Milky Way, we're tracking the orbits of stars around that central massive object. In other galaxies, we're often looking at things like the bulk motion of stars or gas at the center of a galaxy, and looking for the influence that the black hole might have on that material.
When we say the black hole, are there no galaxies known with 2 large ones?
There are some galaxies where we detect binary supermassive black holes. So when galaxies merge, if they each have a black hole, we think that those black holes will eventually merge together as well. So we do observe some systems where there are two supermassive black holes. And there have been a couple where we think there might be 3, which is pretty exciting, but those should all eventually merge, we think. Okay, so we have learned in the last few decades that every relatively large galaxy seems to have a supermassive black hole at its center. Much of this comes from work that has been done with the Hubble Space Telescope, looking at nearby galaxies in our local universe. And every relatively big galaxy that we've looked at, we have found to have a supermassive black hole at its center. And by relatively big galaxy, I mean roughly galaxies the size of our Milky Way and larger. These black holes weigh about between 1 million and 10 billion times the mass of our sun. And despite the fact that they are ubiquitous in relatively large galaxies, there are many open questions about supermassive black holes. Perhaps the most pressing is that we don't actually know how they formed. So we think they must have formed in the very early universe, but we don't know the precise mechanism by which they formed or how large they were when they formed. So presumably they started out smaller than we observe them today, but we don't know exactly how small they started out and how much growing they had to do to get to their present observable sizes. Okay, so this is a very nice diagram that illustrates formation and evolution of supermassive black holes in our universe. So on the y-axis here, we have redshift. So at the top would be the very early universe going down to present day at the bottom. And then we have black hole mass on the x-axis in units of solar masses. So at the top are represented a few different possible formation scenarios for supermassive black holes in the early universe. So these come in a few rough categories. One being population 3-star stellar seeds. So this suggests that the progenitors of today's supermassive black holes would have been the remnants of the deaths of very early massive stars. We can also have the formation of a black hole in a stellar cluster that would leave behind a bit more massive of an initial supermassive black hole seed. And then we have direct collapse black holes, which would have started out at about 10,000 or 100,000 times the mass of our sun already. So these different formation scenarios produce black hole seeds of different masses. So the smallest being those from the population 3 stars, and the largest being those from the direct collapse pathway. So black holes will form at high redshift. They'll grow and merge and produce the supermassive black holes that we observe in the present day universe. And some of them probably don't grow very much or perhaps don't undergo many mergers. And so we should be left with a population of leftover intermediate mass black holes at present day that haven't grown much since their formation. So unfortunately, we cannot yet observe black hole formation in the early universe, but this plot illustrates a few different possible present day constraints on black hole formation scenarios. So that means things that we can look for in the present day universe that might help us distinguish between these different formation pathways. So here we have those three different formation mechanisms. The population 3 stars are in the center, gravitational runaway, which refers to formation of a black hole seed inside a stellar cluster, and then direct collapse, where we have these very massive black hole seeds. So those are kind of the 3 categories of formation mechanism. And then on the right, we have a few different present day observables that we could look for. So on the top is number of black holes versus black hole mass. In the middle is a particularly important one. So this is the fraction of galaxies that contain black holes as a function of galaxy mass. And you'll notice that above a certain galaxy mass, no matter how these black holes formed, basically every galaxy should have one. But for lower mass galaxies, you start to see a difference in the fraction of galaxies that host a black hole, depending on this formation mechanism. And then on the bottom, we have black hole galaxy scaling relations. So the relationship between the mass of the black hole and properties like the mass of the galaxy also might be different for present day galaxies, depending on the black hole formation scenario. And so all of these differences between these formation mechanisms are visible for the population of low mass galaxies. So in order to distinguish between these formation scenarios, we want to look for black holes in small galaxies. So this plot shows a scaling relation between black hole mass and galaxy mass. So black hole mass is on the y-axis and galaxy mass on the x-axis. Our Milky Way would be somewhere in the middle there, black hole around 1 million solar masses. And we want to look for black holes and galaxies down here, galaxies that weigh a few percent the mass of our Milky Way, and black holes that might be 10 or 100,000 times the mass of our sun.
So could you put some numbers on the horizontal axis there?
So in the middle, you might have a galaxy that is has a mass in stars that is a few times 10 to the 10 solar masses. And then the tiny galaxies that we're looking at are a few percent that, so maybe 10 to the 9 or billion solar masses. Okay, we're also interested in looking for black holes in these small galaxies because they're a good place to search for intermediate mass black holes. So I mentioned that we have these 2 categories of black holes that we have observed. These stellar mass black holes at around 10 or 100 times the mass of our sun, and then supermassive black holes that are upwards of 1 million times the mass of our sun. And we haven't observed much in that intermediate range. And we don't know if that's because they're really hard to detect or because they don't exist. So the recent LIGO detection of the 150 solar mass black hole sits down there. And then the black holes that I'm interested in searching for sit up here at around 100,000 times or 10,000 times the mass of our sun. And based on these relations between black hole mass and galaxy mass, we can expect these to reside in dwarf galaxies. Okay, so we want to search for black holes in dwarf galaxies to hunt for intermediate mass black holes. to constrain models of massive black hole formation and to understand how black holes and their host galaxies interact with one another on all scales. Okay, so finding black holes in dwarf galaxies. It turns out that it's really difficult to detect black holes in dwarf galaxies, even when they're very close to us. So these black holes are smaller, they have smaller gravitational spheres of influence, right? So it's more difficult to detect the influence that they have on the stars and gas around them. They're also lower luminosity, so it can be really tricky. This is the Large Magellanic Cloud. So this is a dwarf galaxy that is orbiting around the Milky Way, one of the closest systems to us. And it illustrates how difficult it is because we don't actually know whether the Large Magellanic Cloud has a massive black hole in it or not. So oftentimes when we hunt for black holes, we'll look at motions of stars or gas at the center of the galaxy. With a galaxy like this, it turns out it's actually really tricky to even locate what the dynamical center is. And so even when systems are really close to us, it's really hard to determine whether they have massive black holes at this low mass end. So in order to find black holes in dwarf galaxies, we need to search for those that are active. So those that are accreting lots of material, and that material is heating up and emitting a lot of light from the center of the galaxy. So again, it's tricky to find these systems if they're quiescent because they're low mass, they have small gravitational spheres of influence. And so our only hope for building population statistics currently is to search for active black holes in dwarf galaxies. So these are called active galactic nuclei, or AGN. So the system shown here, NGC 4395, is one of the best studied dwarf galaxies with an active galactic nucleus. This system happens to weigh a few percent that of the Milky Way and has a black hole of about 100,000 times the mass of the sun. And then on the bottom is just an artist illustration of what the disk might look like around an accreting black hole. So this is a really exciting field to be a part of because it's progressed a lot in the last 15 years or so. So in 2004, we knew of only 2 examples of active galactic nuclei in dwarf galaxies. So one of these is NGC 4395, which is the one I showed on the last slide. The other is POX 52. These were both serendipitous discoveries. And in the last 15 years, thanks to really large scale surveys where we've taken observations of tens of thousands of galaxies and multi-wavelength efforts, we've started to build bigger samples comprised of hundreds of examples of AGN in dwarf galaxies. And one thing that I want to stress throughout this talk is that this is very much a multi-wavelength field that relies on a lot of different observational techniques and observations across the entire electromagnetic spectrum, from radio waves to X-rays, and eventually, hopefully, gravitational waves. So I wanted to spend a few minutes just going over the basic characteristics of an active galactic nucleus, so that when I talk about different detection techniques, it'll be more clear. So we have our black hole at the center, and there's an accretion disk around that black hole feeding the black hole. That accretion disk emits light at optical and UV wavelengths, and the photons from the accretion disk ionize the surrounding gas in this broad line region and narrow line region, which I'll explain in the next slide. So the accretion disk emits optical and UV photons, which ionize the surrounding gas. Sometimes you have a radio jet. You can also get an X-ray emitting corona that is surrounding the accretion disk. And then you get emission lines, very strong emission lines at optical wavelengths from the accretion disk photons ionizing the surrounding gas. So a gas that is close into the black hole will generate these broadened emission lines. And so these are just Doppler broadened because the gas that is close in and ionized is close enough to feel the gravitational influence of the black hole. We also get narrow emission lines from farther out. So that's this narrow line region that's farther out from the central black hole. The broad line region is kind of tucked inside there. We think there might be an obscuring torus of gas and dust around the black hole so that you don't always see the broad lines, but we'll always see the narrow emission lines. So this is an example of an optical spectrum of an active galactic nucleus. And in this case, you have those Doppler broadened emission lines from the ionized gas that is close into the black hole, and then your narrow emission lines from farther out. And we can actually use those broadened emission lines to get estimates of the black hole mass because they give us information about how fast the gas is moving in the broadline region. Okay, so these narrow emission lines are often used to identify AGN in galaxies or active galactic nuclei. This is a diagram that's going to come up a few times throughout the rest of the talk, so I want to take time to explain it. Here we just have different ratios of particular emission lines, a couple of hydrogen Balmer lines, and then an O3 line and an N2 line. And the basic premise here is that there's two kind of major things that can ionize gas in a galaxy. Photons from very young hot stars, and then an AGN. So those two phenomena will have very different photoionizing spectra, different proportions of higher energy photons. And so plotting the relative strengths of these emission lines characterizes the photoionizing spectrum of a galaxy. So depending on where an object sits on this diagram, we can determine whether it is likely to have ionization from star formation, from an AGN, or from a mix of the two. So that's the composite region. So this particular plot comes from work Rines et al. 2013, where they looked at a sample of 25,000 dwarf galaxies and analyzed the spectra of all of those and looked to see whether they contained active galactic nuclei. So as you can see from this plot, most of those objects fell in this star forming region of the diagram, and about 150 were found to have some signatures of an active galactic nucleus from falling in this AGN region or the composite region. That might not sound like a lot, but this was a huge increase in the number of dwarf galaxies that we knew to contain active galactic nuclei. One really exciting object to come out of that study was this galaxy RGG 118. So this galaxy has a stellar mass, a few percent that of the Milky Way. It's this cute little spiral galaxy, as you can see in its Hubble Space Telescope imaging. And its narrow emission line ratios tell us that there is an active galactic nucleus present. This galaxy was also found to have these broad emission lines. So this is zooming in on one of those broad emission lines with a width of about 800 kilometers per second. And using this broad emission line, I was able to find that this system has a black hole weighing just 50,000 solar masses. So this is one of the smallest black holes that we've found at the center of a galaxy. Since then, we have found other black holes of a handful of other black holes with similar masses of around 100,000 solar masses or a little less. But these systems are really exciting and start to kind of push down on that intermediate mass black hole regime.
Can you explain what is increasing at 1% of its mass?
Oh yeah, sorry. So we also obtained X-ray imaging and found that this system has pretty strong X-ray emission, which is also really good confirmation that there is an active galactic nucleus in this system. And then every black hole has a theoretical maximum limit at which it can accrete. It's called the Eddington luminosity. And that can be estimated from the X-ray luminosity that you find. And so we found that for this system, it's accreting at about 1% of that maximal luminosity, which is pretty rapid accretion for this tiny black hole.
And how do you find the mass from the spectrum only?
Yeah, so the width of the broad emission gives you the velocity of the gas in the broadline region. And then there's a few different steps that you can take to get the distance to that gas from the central black hole. But it turns out that the luminosity of that broad emission is correlated with the distance to those clouds in the broadline region. So then you have your velocity and your distance, and you can get an estimate of the mass. Okay, so while these optical spectroscopic techniques have been successful and identified a lot of really interesting objects, we also think that they're limited. So these techniques were derived for galaxies at higher masses and not really designed to be used for low mass galaxies. And so we think that samples selected using just those techniques might be incomplete. One way in particular is this issue of metallicity. So here on the bottom, I'm showing again this diagram with the emission line ratios. It's called the BPT diagram. And what this plot is illustrating is that as you decrease metallicity, an object can actually shift from the right or the AGN region of the diagram over to the left in the star forming region of the diagram. And metallicity in astronomy is just basically the fraction of stuff you have in a galaxy that is not hydrogen or helium. So if you have a galaxy that has lower metallicity, even if it has an active galactic nucleus, it might not be selected using this diagram. Another issue is that if you have a relatively low luminosity active galactic nucleus, other stuff in the galaxy might dilute that signal so that you don't detect it. And this is an issue for dwarf galaxies because these galaxies tend to have lower metallicities than high mass galaxies. So this is showing what's called the mass metallicity relation. Metallicity on the y-axis, galaxy mass on the x-axis. And as you move to lower mass galaxies, they tend to have much lower metallicities than their high mass counterparts. So that's one reason why this diagram might not always select active galactic nuclei in dwarf galaxies. So in order to not miss a substantial fraction of this population, we want to look for other ways of detecting these objects. So this is a truly multi-wavelength effort. There have been lots of great studies done at a variety of wavelengths using lots of different detection techniques for finding AGN in dwarf galaxies. I'm going to focus today on some work that I've done using optical photometric variability to search for AGN in dwarf galaxies. Okay, a very nice property of active galactic nuclei is that they tend to vary over time. So we have the accretion disk around the black hole, and there's instabilities and turbulence in the accretion disk that lead to variations in the light output over time. And these are actually detectable on human timescales. So these variations can occur on timescales of days or weeks. So on the right there, we have a light curve of a well-studied active galactic nucleus. And so that's just showing the brightness of that AGN over the course of about 8 years. And you can see that its flux varies by about a factor of 2. And we see this variability at a variety of wavelengths. And it's especially relevant right now because we're in kind of a golden age of time domain astronomy. There are a lot of publicly available repeat imaging surveys, meaning surveys that will image the same regions of sky over and over again over the course of years. And very soon we'll have the Vera Rubin Observatory, which will do this on a much larger scale. So there's lots of data where we can look for variability in large samples of galaxies. So my goal is to use this optical photometric variability to search for AGN in small galaxies. I've done this using a couple of publicly available repeat imaging surveys so far, but I'll discuss them as a unit. So these two surveys are the Stripe 82 survey, which was run by the Sloan Digital Sky Survey and covered an area of about 300 square degrees between 1998 and 2008. And then another survey that I've looked at is the Palomar Transient Factory, which operated from 2009 to 2017 and covered a much larger area of sky, almost the entire visible northern sky, about 30,000 square degrees. And in these two surveys, I searched for variable active galactic nuclei in samples of tens of thousands of nearby galaxies. To give you an idea of the kind of data that was available, these are a couple of histograms showing the number of galaxies versus the length of the light curve on the left. So most galaxies had light curves spanning several years, up to about 8 years. And then on the right, we have number of galaxies versus data points. I put a lower limit on the number that they needed to have in order to analyze, but some galaxies had as many as 1,000 observations that we could use to search for AGN variability. So there's just a real wealth of data that was available with which we could do this work. In order to detect variable AGN in dwarf galaxies, we need to be able to look for very subtle changes in the light output from the center of the galaxy. So to do this, I used a technique called difference imaging or image subtraction to achieve very accurate differential photometry and look for a sometimes weakly varying source that is superposed on top of the host galaxy. So the basic steps here are first to construct what is called the template image from your best frames. So you take your best seeing, highest resolution frames with the lowest background and combine them into a very high quality template image. From there, you take each individual exposure and you degrade the template image to match the resolution of that individual exposure. Then when you subtract the two, you're left behind with a difference image, which should be flat, just pure noise, unless there's something varying between the template and that individual exposure, in which case it will pop out as bright or dark against the background. So from there, I would measure the light at the position of each of the galaxies that I was looking at in the template and difference images to construct a light curve, which just shows us the light output from the center of the galaxy over time. So here I'm showing an example of a galaxy that was not variable. So you can see in the little video on the top of the difference images that nothing is popping out against the background noise. It's just a non-varying source. And then on the bottom there, we have the light curve, so the brightness over time for this particular object over about 2,000 days. And then here's an example of a galaxy that was found to be variable. So you can see very clearly here in the difference images, as the galaxy gets fainter, we get these darker spots and then gets brighter there at the end. In order to search for AGN variability, we also search for objects that are well fit by a damped random walk model. So a damped random walk has been found to be a really good empirical descriptor of AGN variability. And so what's shown in the blue shaded region on top of the dark gray data points is the best fit damped random walk model. So in order to make sure we're just selecting variable active galactic nuclei, we look for objects that are both variable and well described by this model, which again has been found to be a good empirical descriptor of AGN variability. And this helps us weed out other variable phenomena like supernovae. So after looking at these tens of thousands of nearby galaxies, we ended up finding over 250 variability selected AGN in low mass galaxies. These are a couple of my favorite examples. So the one on the left is the lowest mass galaxy that we found to have AGN-like variability. So it's a few orders of magnitude less massive than the Milky Way. And you can see from the light curve that it's both variable and well described by our model of AGN variability. The one on the right, I think, is interesting because it has this kind of neat morphology with this kind of cool off-center knot, which is where the variability is actually occurring in this system. So these are a couple of examples of the more than 250 low mass galaxies that we found to have variable active galactic nuclei. So we also looked at where these systems sat on this narrow emission line diagnostic diagram. So shown here are the positions of the galaxies from this sample that were found to have variable active galactic nuclei. And they are color-coded by their stellar mass. So the most massive galaxies in the sample are yellow, and then the dwarf galaxies are color-coded blue. And what I found was that for the massive galaxies, basically everything that was found to be variable or have a variable AGN also fell in the AGN or composite regions of this diagram. But for the lower mass galaxies, many of those that were found to have variability selected active galactic nuclei fell in the star forming region of this diagram, which indicates that these are systems that would have been missed by other selection techniques. So we're finding a complementary population of AGN in dwarf galaxies than is found by these more standard AGN selection techniques. We also wanted to look at how the fraction related to the galaxy stellar mass. So here I'm showing the fraction of galaxies with a variable active galactic nucleus as a function of galaxy mass. The red shaded region is just where our sample was incomplete. So that's why the error bars are much larger there and why we have that artificial downturn at the end. But what you see is that there's this trend where the fraction of galaxies with a variable AGN seems to increase with increasing galaxy stellar mass. But this could also be a selection effect since it's easier to detect variable AGN in brighter systems, so galaxies with a brighter apparent magnitude. And since the lower mass galaxies in our sample are also fainter, it'll be more difficult to detect AGN in those systems. So on the right, we have variable AGN fraction versus the apparent magnitude of the galaxy nucleus. So brighter is on the left and fainter is on the right. And as we move towards fainter galaxy nuclei, our fraction goes down. So we need to take this into account in truly looking at the variable AGN fraction as a function of galaxy stellar mass. So in order to account for this apparent magnitude effect, what I did was to construct subsamples of lower mass galaxies with the same brightness distribution as the higher mass galaxies. So here I'm showing a few different histograms for different galaxy samples as a function of galaxy brightness. So massive galaxies are shown with the gray histogram. The intrinsic magnitude distribution of lower mass galaxies is shown in red. And then we drew subsamples from that distribution that matched the brightness distribution of the higher mass galaxies and computed the fraction of variable AGN in those subsamples. And when we do that, we find something interesting. So for galaxies with stellar masses above 10 to the 10 solar masses, so these are pretty massive galaxies, the fraction that have a variability selected AGN is about 1.5%. And then when we do this accounting for the different magnitude distributions, we find that the fraction for galaxies between 10 to the 9 and 10 to the 10 solar masses, so we're getting into that low mass dwarf galaxy regime here, we find a fraction of about 1.4%, which is consistent with those higher mass galaxies. For the lowest mass galaxies in our sample, we do see a drop, but the galaxy catalogs at those masses are also incomplete, so more work needs to be done there. But we do find that at least down to stellar masses of 10 to the 9 solar masses, the fraction of galaxies containing a variability selected AGN is constant. And so this is relates back to those figures I showed at the beginning of black hole fraction versus galaxy mass, and how we can distinguish between these different formation mechanisms. And so that transition is expected to occur at around 10 to the 10 solar masses. So we're starting to be able to place some constraints on this. And this is the fraction that have a variability selected AGN, right? It's not necessarily the fraction that contain a black hole at all, but it does suggest that the overall fraction of galaxies containing a black hole doesn't drastically change down to at least stellar masses of about 10 to the 9 solar masses. So there have been some other studies that have found similar results in terms of these different selection techniques. So this is a really interesting plot from Burkhall 2020, where they looked for X-ray emission from nearby dwarf galaxies. So based on the X-ray emission of these systems, they identified about 50 dwarf galaxies that had AGN. And what's shown on the right is, again, this diagnostic diagram. The colored points show the positions of these X-ray selected dwarf galaxies with AGN. And again, many of them don't fall in these AGN or composite regions of the diagram. So this really demonstrates how we need to bring together a lot of different selection techniques to have a complete understanding of this population of active galactic nuclei in dwarf galaxies. So ultimately, what we want to know is the total fraction of dwarf galaxies that contain black holes. And to move towards this, it would be really helpful to understand where these different selection techniques overlap with one another, what types of galaxies each selection technique works better for. And to do this, we're going to want to study the properties of the host galaxies and the black holes that are selected with different techniques. So on the right is just a really initial effort to look at differences in galaxy properties between dwarf galaxies with AGN selected through different techniques. So these two histograms show the color distribution of dwarf galaxies with black holes selected through variability and those optical spectroscopic diagrams. So the variability selected AGN in dwarf galaxies tend to be bluer, and this suggests that they have more star formation, which could be diluting the signal from the AGN in those emission lines. So that might be why these galaxies with the optical spectroscopy tend to be redder, because they have less star formation, so you can more easily see the emission line signature of the active galactic nucleus. Something I'm really excited about is that we were awarded Chandra X-ray Observatory and Hubble Space Telescope observations to really look in detail at some of these variability selected AGN in dwarf galaxies. So this is a sample of 9 galaxies that we're obtaining observations for. And with these X-ray and Hubble Space Telescope observations, we'll be able to search for X-ray emission from these systems and characterize the host galaxies in much more detail. Okay. Something I wanted to touch on briefly are some efforts to look at these scaling relations between black holes and host galaxy properties. So this is another area where we might see differences in the present day population of black holes and their host galaxies, depending on the dominant formation scenario. This example is showing what we might see for black hole mass versus galaxy mass, but there are other scaling relations that we can look at as well. So this is what's called the M sigma relation. It's the relation between the black hole mass and the velocity dispersion of stars in the host galaxy. So this has been found to hold for higher mass galaxies, and we wanted to see whether this held also for dwarf galaxies with black holes. So on the left, I'm showing an example of one of the dwarf galaxies that we added to this scaling relation. So the bottom there is showing different absorption lines in the optical spectrum of the galaxy. And from those absorption lines, you can measure the velocity dispersion for stars in the host galaxy. So we did this for 8 galaxies in this work, 8 dwarf galaxies down here, and found that they're consistent with this scaling relation that is found for much higher mass galaxies. So this provides another important constraint for these black hole galaxy scaling relations and black hole formation mechanisms. Okay, so for the last couple minutes here, I just wanted to mention a few different avenues for progress with different upcoming astronomical facilities. So I'm really excited about the Vera Rubin Observatory, which is going to carry out the legacy survey of space and time. This is scheduled to begin operations in 2023. And the Vera Rubin Observatory will image the entire visible night sky every few nights. So we'll really have kind of a movie of the night sky. We'll generate a huge amount of data. And with these observations, there's a lot of science goals that are going to be addressed. We'll be able to study the nature of dark matter and dark energy, search for near-Earth objects, and then of course study the transient and variable sky. So look for things like supernovae, look for stars that are being disrupted by supermassive black holes, and then for my interests, look for variable active galactic nuclei. So this will be an 8.4 meter telescope and is scheduled to begin in 2023, so just a few years. And then hopefully eventually we will have LISA, the Laser Interferometer Space Antenna, space-based gravitational wave observatory, whereas the ground-based gravitational wave observatories have arm lengths of a few kilometers. LISA would have arm lengths of about 2.5 million kilometers and would kind of trail Earth in a heliocentric orbit. It would be able to detect a very different population of merging objects than the terrestrial gravitational wave observatories do. So on the right is a plot showing what different gravitational wave observatories are sensitive to. So LIGO can detect things like merging stellar mass black holes or neutron stars, and LISA would be able to detect mergers of 10 to the 6 solar mass black holes with other compact objects, and would be sensitive to merger products between about 1,000 and 10 million times the mass of our sun. So might be able to detect black hole seeds at higher redshift through their gravitational wave signals. Okay, I'd like to leave you with a few takeaways. So dwarf galaxies are a great place to hunt for intermediate mass black holes, which have so far been fairly elusive. Their black holes may be the relics of early universe black hole formation and can thus help us distinguish between different black hole formation processes. Black holes in dwarf galaxies are really tricky to find, but there are a lot of really exciting, creative, multi-wavelength searches that are going on. And we're starting to provide some meaningful constraints on the fraction of dwarf galaxies that contain black holes and the masses of black holes that reside in dwarf galaxies. So, thank you.
Thank you for a wonderful talk. So we'll take questions, and over Zoom, you can raise your hand. I'll see if there's volume here, or type in the chat.
Is there a correlation between these things and the morphology of the host galaxy, whether they're elliptic or spiral?
Can you repeat?
Yeah, sure. So the question was whether there's any correlation between the presence of a black hole and the morphology of the host galaxy. It's a great question, and there's no clear answer to that yet. And part of it is that the spiral galaxies tend to have more star formation, so it's going to be harder to detect black holes in those systems, in those dwarf galaxies. But I will say that we do find black holes in dwarf galaxies spanning a wide variety of morphologies. So there's no clear correlation, but it is more difficult to find them in these more strongly star-forming systems.
Okay, Crystal Martin has a question.
Hi, Vivienne. That was a great talk. Thank you.
Hey.
I was really struck by how the galaxies in the star forming part of the BPT diagram could be AGN host. I'm wondering about in the other direction. I mean, are there many objects that fall in the AGN part of the BPT diagram that, despite having AGN-like line ratios, do not show X-ray emission and do not show variability, and therefore might be in that part of the diagram for reasons like shocks that are totally unrelated to the AGN?
Great question. So in case anyone couldn't hear, the question was whether any of the dwarf galaxies that fall in the AGN region of this spectroscopic diagram could be kind of false positives. So we haven't found any examples of that. And the galaxies that we've looked at in the AGN region that have broad H-alpha emission all show strong X-ray emission consistent with being in AGN. Some of them show variability. Not all of them do, but that's to be expected with kind of the sensitivity of current repeat imaging surveys. So we think that the objects that do fall in the AGN region are pretty secure.
William Mandel with a question.
Hi, thanks very much for a great talk. I had a question about the mass measurement. So if I understand correctly, one of the ways of measuring the masses is by looking at this broad line region and inferring from that the mass, but I think that requires two different calibrations, one between luminosity and distance, and one between the, sort of a correction factor in Kepler's law, if you wish, between the actual width of the region and the mass. And I guess the two questions were, one, how confident can we be that the empirical scalings there are still valid for lower masses? And in particular, do you feel that there is possibly a minimum limit to the mass where this kind of extrapolation will be safe? So, is there a threshold to the lower level of the masses you can probe in this particular way?
Great question. So the question had to do with the black hole mass measurements that we have. These rely on correlations that have been calibrated only for more massive systems. And so there is a question of whether they can extend towards these lower mass black holes. So it's definitely true that we rely on these calibrations that have been done for higher mass galaxies and have some scatter. So the black hole masses that are measured in this way are uncertain to about a factor of 2 or so. They have been found to hold down to black holes of about 10 to the 6 solar masses. So not that far off from these kind of 10 to the 5 solar mass black holes that we're looking at. What you really want to be able to do is check different black hole mass measurement techniques against one another. So you want to be able to do this broadline mass and also get a dynamical mass. Unfortunately, there's basically only one system that we can do this for, that's NGC 4395. Luckily, the different mass estimation techniques are found to be consistent with one another for the black hole in that system. I don't think there's any reason to expect that these calibrations don't hold down to these black hole masses, but it definitely is an assumption, but is also the only way that we have of measuring black hole masses for these systems.
Just a basic question is what stops the black holes, I mean, bigger galaxies from just getting bigger and bigger? Is it that they just basically deplete so much of the material around them? There's nothing more for them to accrete, or other mechanisms?
Yeah, this goes to a question of AGN feedback. So it's thought that basically feedback from the central AGN can remove gas from the area and prevent the black hole from growing more, and that this might drive some of these scaling relations between the black hole mass and the galaxy mass.
Are there any more questions? Okay, if not, let's thank Vivienne again.
Yeah.
Thank you.
Thanks.
Excellent.